Hi, this is Professor Ross, and we're here to talk about least squares regression. This is the second part out of two videos talking about least squares regression. In our previous video, we talked about what a linear model is, how we can interpret the slope and the intercept, how we can use it to make predictions, and how we can also look at the quality of the model and see how good it is. And finally, we started looking at how to calculate errors in predictions. And we ended looking at this scatter plot. Here is carbon emissions and South Pole temperatures, and we said here's a linear model for that data. And each piece of data doesn't necessarily fall on the line. Some fall very close, maybe on it, but lots of the data falls off of it, so there's error associated with each value, each piece of data. And a good model minimizes that error, makes it as small as possible. Now, here's something interesting. If we would take all the errors, we can calculate a number that tells us how far off each of these are. All the ones below here are actually negative errors, and all the ones above it are positive errors. If we say let's see how much error there is altogether by adding it all up, guess what happens? All the error cancels out in the best line. So that's kind of problematic. And so what statisticians said is, instead of paying attention to the positive errors and the negative errors, they were clever and they said, let's square the errors. If we think about the square of the errors, we no longer have negative values. And then when we add them all up and we try and look at the total error, we no longer have it all cancel out. And so that's why we call the best fit regression line, in some sense the model that reduces all that error as much as possible, we call it the least squares. Because we don't just try and reduce the error, we reduce the squares of the error. Just like standard deviation. We needed to square the errors so that they were all positive. We do the same kind of thing here. The least squares regression line is the one that makes the sum of all the squares of the errors as small as possible. And so that's the line that we use to model the data. And there's a lot of different ways we can calculate the least squares regression line. You can calculate it by hand, and here are the formulas for doing that. And it's not bad to try it out once or twice. But for the most part, we want to be able to use our calculator and use SPSS. How do you do it by hand? One thing I just want to take a quick look at here is you're looking for this equation, y equals an intercept plus a slope times x. And so we can calculate the slope with this formula. B1, the slope, is correlation times standard deviation divided by standard deviation. Standard deviation of y divided by standard deviation of x. Those are important numbers that we've been looking at all along, correlations, standard deviations, and they give us the slope of the least squares regression line. Look at the intercept. The intercept says take the mean of y minus the slope times the mean of x. Once again, two very important numbers for us. So the least squares regression line is based on correlation, standard deviation, mean, all calculations we've been using, and also all very sensitive calculations. And so that's going to be something we see down the line. This equation is very sensitive to any outliers. Let's talk about how we can do it with a calculator. If you've got yourself a TI graphing calculator, the place to do it is going to be in the stat menu. And actually, let's go ahead and take a look at a set of data and see how we can do that. So here's some data. These are years from the Olympics, 1964 through 84. You can see they skip every 4 years. And here was the gold high jump recorded for each of those years. Let's use our calculator and use SPSS to calculate the least squares regression line. First, real quick, before you do that, it's always a good idea to take a quick look at the scatter plot. So here's a scatter plot of that data. Here's the years 1960 to 85, and we can see how the high jump went every 4 years. And it looks like a linear regression line would be a pretty reasonable model for this. So let's go ahead and calculate it. How do you do that with a graphing calculator? Well, what you want to do is turn it on and go to the stat menu, and you want to enter your data under edit. So you go ahead and choose edit, and your explanatory variable, you want it L1, and your response variable you want in L2. I've already entered those. You can pause the video and enter them now if you want. Once they're entered, you want to choose Stat and go to Calc, and you want to scroll down until you see lin reg. Now be careful, you don't want ln reg, you want lin reg. And there actually, you may see two of them. If you scroll down a little more, here's another lin reg. They just give you the slope and the intercept as different letters. So it doesn't really matter as long as you're paying attention to your output. I'm going to choose the first one here. And it says which list do I want to use, L1 and L2. I don't have to worry about a frequency list or storing anything. I'm just going to go down to calculate and hit enter. And here it is, my linear regression equation. Y equals ax plus b. A is going to be the slope for this output, and b is going to be the intercept. And here it lists a for me, 0.34285. So my slope is this number, 0.342x, plus, and here's my intercept, negative 587. So that's how I can get my regression equation with the graphing calculator. You can see it also gives me r squared and r as well. So we get a lot of nice output here. How can we do this with SPSS? Well, you need to enter the data into SPSS, so I've actually already done that by hand here. And one thing to do whenever you enter some data, look at the variable view and make sure that everything looks good here. You can make sure it's named the way you want. It has the right decimal places for what you want, but the big thing is to go to the measure and make sure these, since they're numbers on a scale, we want to set the measure to scale. What do we do once we are all set there? Simply go to Analyze, Regression, and choose the linear regression. The dependent variable is our outcome, it's our response, and that's going to be the gold high jump for that year. And what we're trying to use as our explanatory, the independent variables, is the year. So we're going to see if our year explains why the high jumps were going up. And let's just go with the default stuff. We don't need to choose any of these other options. Let's just click OK. Here's our output menu, and we can see we get quite a bit of stuff showing up under regression. We get the variables, we get a model summary here, we see R squared, so that's kind of nice to see that output as well. There's a box called ANOVA we don't need to worry about. Down here in coefficients is where we're going to see the two things we want to see, the slope and the intercept. So in the top row of the coefficients, it's parentheses constant, and the coefficient that's a constant that's not multiplied by anything is our y-intercept. And we see it's the same as it was on the calculator, negative 587. And the coefficient for year is our x variable, so what's times x? That's the slope. And so we can see the slope here, same as on the calculator, 0.343. So the two numbers, the slope and the intercept, show up in this coefficients box, and the intercept is always the top number and the slope will be the bottom number. So that's how we can find it in SPSS. We can actually see it also in SPSS if we go to the graph and we add that equation line. It'll actually show up here. And if you're not sure how to do that, there's another video on how to add that regression equation line to the graph on the how-to video. So check that out. Here we go. We can now calculate it a couple different ways. Interpret it. What does the slope tell us? What does the intercept tell us? Let's figure it out. Y equals, here's the intercept, and here's the slope. Let's try the intercept first. Negative 587.55 tells us this line crosses the y-axis at negative 587. Let's take a look at the picture. If I trace this line all the way back to the y-axis, and now it looks like the y-axis here, but it's not really. This is actually not when x is 0. This is when x is about 1955 or something like that. If I want to go all the way back to where x is 0, I'd have to go way, way, way down there, a long ways. And what that equation is saying is I would end up at negative 587 when I went down there. What's the interpretation? Well, the x variable is year. So what we're saying is if we go to year 0, the high jump gold, our model would predict negative 587. Well, that's just silly. The Olympics weren't going on in year 0. Nobody could jump negative 587 inches, so not very useful interpretation there. But the slope is always a useful interpretation. The slope is the number times x, and it says 0.343 is our slope. How do we interpret that? This is the rise when we have a run of 1. So it's like 0.343 over 1. And so this line is going up 0.343 for every 1 we're going over. We got to connect that to the context. So we got to say, what is that telling us about years in high jump? Every time the year goes up 1, we do a run of 1, the slope says you rise 0.343 inches. So every passing year, our model predicts the high jump goal to be going up about 1/3 of an inch. And that's exactly what's happening with this line here. And it actually is a pretty good prediction. We see over time, we keep going up about 1/3 of an inch every year, and it does a pretty good job of telling us how we're going to land each 4 years down the line. So the slope is a nice way to interpret this data. It says over time we're seeing a gradual increase of about 1/3 of an inch every year, and that's an important interpretation that this regression line tells us. Let's try another couple ones to interpret. Here's highway miles per gallon versus city miles per gallon. Here's the least squares regression equation. Y equals 5.01 plus 1.12x, an R of 0.973, and R squared of 94.7. What's going on here? We're seeing that the intercept is 5. What that's saying is if city miles per gallon were 0, highway miles per gallon would be 5. Well, no cars get 0 city miles per gallon, so not very useful. But 1.12, that says if your city miles per gallon goes up 1, the highway would be predicted to go up 1.12. In other words, just about the same. So as city miles per gallon go up in cars, highway miles per gallon go up about the same amount. R being 0.97 is very close to 1. That means it's a very strong linear correlation. And R squared of 94.7 tells us the same thing in general. This is a very strong linear model. Specifically, we say we can account for 94.7% of the variation in the highway miles per gallon based on our model of city miles per gallon. So in other words, if I know the city miles per gallon for my car, I can explain almost everything there is to know going on with highway miles per gallon. How about this set of data here? This is NBA income versus value. The NBA values, that's how much for example, you could sell the team for if you were trying to sell the NBA team. The income, in contrast, is how much money they bring in over a season. So we can see that there's a linear regression model here. Here it is, y equals negative 14.4 plus 0.0777x, an R of 0.211, and an R squared of 4.4. Let's look at R and R squared first. R, a lot closer to 0 this time compared to our other model. So this is a lot weaker model. This is a relatively weak model for this data, and maybe it's this outlier that's part of the problem. R squared is very low, 4.4. So once again, a weak model, but specifically, this is saying we can only account for about 4% of what's going on with these incomes for these teams based on the value of the team. In other words, the value of the team is not telling us very much about how much income they're making over time. The model itself, how do we interpret the intercept, negative 14.4? That says if the value of the team were 0, we would expect that they would lose $14.4 million per year. And so do we really have any NBA teams valued at 0? Probably not. More interesting is the slope. 0.0777 says if your value goes up $1 million, we would expect your income to go up a little bit, about $77,000. And so that's interesting to see a little bit of an increase for higher value teams, but once again, not a great model. Overall, we calculate least squares regression models to help us understand the relationship between two variables. We interpret both the y-intercept and the slope of those, and usually the y-intercept, sometimes helpful, slope always. We can use them to predict but not extrapolate, and we evaluate by looking at R squared.